A lot of people wanted a tutorial after seeing the Skull Island video. Today, I'll show you the basic steps of how it was made. First, open Houdini at the object level, create a geometry node, then dive inside to enter the SOP environment. Then create a head field. Change its size to 8192. Then find the quick brush, create a PSD file node. Now you see the PSD file to import. Importing a PSD file reads alpha by default. You can also read NGB, read alpha. Basically put the name of each layer, become an altitude field. If it is a reader GB, then it will have more layers. Read its GBA separately. We just need to read alpha here. Detailed parameter description. You can take a look at the small question mark here, the help documentation below. The document is bilingual in Chinese and English. Its main function is to read the PSD file and convert it into a height layer. Let's check the imported results. It rotates here. You can rotate this picture. If you modify the PSD file during production, you can click to reload. Reload it. Mark it. After loading in, we first put the general outline of the island. Make it. Mark it. And then we read the mountain. Create a PSD to mountain. PSD to mountain can actually read PSD files directly, and the functions exactly like this node. It actually has this node built in. I'm only using a separate PSD node here out of personal habit. In reality, the two methods are completely identical. This parameter is the default resolution scale. It controls the computational accuracy of this mountain. We lower it a little bit here. It can be calculated very quickly. You can click on its help document to take a look. When adjusting by default, this SDF method can use distance directly. We'll stay in the fast preview mode for now, and only switch to solver based at the very end to save on calculation time. The system is based on iterations to achieve the final result. Its details will be more natural. Here's the drawn file in the PSD. First, we create a new layer. Read this mountain layer called M1. Adjust the parameters. If you think this accuracy is not enough, can be raised a little bit. Let's take a look at the effect of becoming solver-based. It looks a bit rough right now because I haven't run an erosion pass yet. We'll apply the erosion solver globally once the main shapes are finished. Do a little smoothing. Point to the relevant parameters. There is generally also help documentation above. Add a new layer. Read the layer of the second mountain. Adjust parameters. The worst part of traditional workflows isn't building, it's editing. That domino effect, where one tweak ruins the whole project, is a total nightmare. This solution changes the game by turning a high-threshold process into an accessible toolkit. If you can draw a sketch and know the Houdini basics, you're in. We aren't just cutting down man-hours. We're empowering every single indie dev to play God over their own digital world. After quickly adjusting these mountains, let's go a little bit further. Change this SDF method to solve-based, settlement-based. The accuracy is higher now. Now we add the erosion effect. For example, give A10. So I'm done, so let's get a little fuzzy. Make it smoother. And that's basically how the mountain is made. If you change the parameters while the erosion solver is on, you'll need to click Reset Simulation, otherwise, the results won't refresh. Mark it. And then we'll extract the erosion. Don't forget to create this height field first. Ocean height field. The ocean altitude field is now available. Ocean mark. Let's create a fully automated road network system. First, we need to exclude the ocean areas, since roads obviously can't be in the water. The more area you exclude, the faster the calculation will be and the less memory it will consume. Exclude the ocean. We should get rid of all rivers except the oceans. Then the main road needs to tell him, what are the layers of the castle? The castle is CST1, the castle door is a door. The main road has no guideline, so skip that. But we have two bridges, Bridge 1 and Bridge to the suspension bridge. You must include them in the setup, or the road won't be able to find the bridge connections. For the secondary roads, you'll need to specify the locations of the villages. In the PSD file, the areas painted in pink represent the village locations. A village generates only one secondary road. The path step is just the distance between points. If you turn this down, you get more points and longer wait times, because it has to iterate through them one by one. So, let's set this to 6. This is the minimum and maximum width of the door. Some painted areas are wider than others, so I'll limit the range here to ensure they stay uniform. Here we all give him a 3.5. Because of our door, the building block is this width, so it fits just right. This is a range scanning radar. Let's make it bigger for him. Radar controls the main road's detection. It has a huge impact on behavior, so make sure to adjust this value carefully. This is a real radar. It detects waypoints and the roughness of the terrain. For example, it will bypass the place where there is no waypoint and try to find the place where there is waypoint. It will try to find the flat place. This is the radar range detection. It is recommended to set this value to approximately twice the path step for optimal results. If the maximum corner value is set to long, the turns will be extremely sharp. Let's cut that at 35 degrees. This value is in degrees, while the path step unit is meters. Well, that's about it. Let's ask him to calculate first. The calculation takes around 3 to 5 minutes, because it involves high-density waypoints and a custom Dijkstra variant for actual pathfinding. It actually took longer than I expected. This node is calculated. That's the white line up there, floating in the air. Shows the link relationship between the main read nodes. This is mainly used for debugging. If the final path does not meet expectations, check whether it's due to incorrect connectivity or missing connections where the road should have linked. This white curve will not be output. The side road curve is meant to transition smoothly into the main road. However, due to low curve precision, a segment of the path is missing. In traditional large-scale terrain development, adding or moving a level is extremely costly, as it requires manual rework of roads, vegetation, and terrain over a vast area. In contrast, this automated road system makes iteration virtually painless. You simply make a few quick edits in Photoshop, and the system regenerates everything in one click with incredible speed. The current system fully supports Linux. On Linux, the Dijkstra implementation is over 30% faster than on Windows due to platform-specific optimizations. If you use Linux as a remote backend, you can offload the computation, submit the job to the Linux server, let it handle the heavy lifting, and then bring the data back to Windows for editing. This approach is much more time efficient. Tailored optimizations have been applied for the Linux platform. Let's take a look at the data from the second port of the RED network system. It outputs raw RED data, which includes both the level positions and the bridges. For instance, these longer segments represent the bridges, while the curves surrounding the level are decomposed from standard pixels in the PSD file. It is not closed at the door, because here is the component to put a door. Here, because of the resolution scale we use, that's down to 0.3. The low precision causes some shape distortion. While increasing the precision would fix this, it would also significantly slow down the process, so we'll keep it as is for now. Next, we extract these curves of the bridge. To generate an arch bridge, let's look at the road level. Marked with numbers, 1 is the main road, 2 is the side road, 0 is unmarked, like those fences. Then this bridge is 5. We took the bridge out alone. While this workflow significantly lowers the entry barrier, a foundational knowledge of Houdini is still required. Otherwise, things can still get a bit tricky. We remove the output point. And then there's just the bridge. We do a length calculation for the length of the bridge. More than 100 this part is the suspension bridge. We also need to extract the arch bridge. We'll take that curve and generate an arch bridge. Add arch bridge none. Let's take a look. Here you can load the template file of the arch bridge. We'll operate it in a while. Here are the default parameters. Open the help document. The colored meshes you see here are generated directly. Everything else on the bridge deck is generated using scattering rules. The specific models being referenced aren't visible here. Instead, they are displayed as bounding boxes. Hovering your mouse over it will bring up the documentation for a quick read. Like this setback. Let's take a look at this parameter. Make it a little bigger. He would set aside a certain distance between the ends of the bridge. And then this is the width of the bridge. Arch height. This will make the place a little smoother. You can take a look at the display here. This might look like an error, but it's actually just a display glitch. The final output will be perfectly fine. Here is the distance from the top of the hole to the bridge deck of the bridge. Here is each hole width. There's a fall-off here. You can adjust the width scale from the middle arches to the edges. With a low setting, the size tapers off quickly. If you turn it up, the arches will stay roughly the same size. And that's basically it. This is where it is added to the material. Different colors represent different materials. Naming each region individually would be too tedious and confusing. Instead, we're using color coding to define which material goes where. Here are some rules. Like the dots on the road. Let's do it in general. We create an asset. The width of our current arch is 10 meters. Its width is 2 meters. 10 meters. The height is half a meter. Simply adjust the parameters. For details, these parameters can be referred to directly. Help documentation. The documents here are in both Chinese and English. Let's focus on this. We're going to load a JSON file for a bridge that we configured earlier. We just click to load the template. It will load successfully with the previous file. It's essentially reusing a template. Of course, we can still tweak the parameters. The data just overrides all the current values here. For example, now the material is also available. Parameters have also been reset. But if these parameters are reset, you can write it here. Also specify a JSON file, output JSON, and you can write it out. Writing and writing are separate. If you use the same one, it will be duplicated, so it's separated here. Detailed introduction inside. There will be a dedicated summary to share this part, because what's completely reusable here is the function of the 3 dots on the dotted line. So I won't go into detail here. Waiting to talk about curves in detail. Let's explain the meaning of this parameter in a unified way, and how it's used. Added 1 or 2 little lines, here, just these 2. Because you can't see the assets anyway here, so here is just a box instead. And that's basically it. Let's reload it. For example, I also made a 3. Configure another file. The arches are large enough for a person to stand upright, and they feature a step surface. Import it. Now that the bridge is set up, we'll pass its mesh data to the river system. This allows the water to interact with the piers, letting them influence the flow map for a more natural look. The video was running long. So I'll be covering the river part in the next video instead.